Hello everyone, I'm Bo Wang. The title of our work is Singular Fourier Decentralized Formation Control for Heterogeneous and Actuated Surface Vessels. This is a joint work together with my advisors, Professor Sergei Nesesov and Professor Hashem Ashrafyun. This talk is divided into these 5 parts, so we'll start with the motivation and the problem formulation. Then we will talk about the main part, which contains the feasible formations, the reduced aerodynamics, and the nonlinear control design. We will show some simulation results, and in the end, we will conclude. So, autonomous vehicles are widely used in civil, industry, and military. While single vehicles performing solo missions will yield some benefits, greater benefits will come from the cooperation of teams of vehicles. In particular, operating multiple vehicles as a team enhances efficiency and increases robustness. There are generally 2 cooperative control schemes, the centralized and distributed. The centralized scheme needs centralized planning and coordination, while the distributed scheme needs only neighbor-to-neighbor interaction, which is more scalable in practice. There are several challenges associated with this problem. The first one is the requirement of distributed control. That is, only neighbor-to-neighbor information exchange is available. Secondly, the vehicles in a network may be described by different models due to the various sizes and structures. Furthermore, almost all vehicles in practice are under-actuated, so the control loss with full actuation assumption will be impractical. And last, in many situations, the GPS signal is not available, while onboard sensors can provide measurements, so it is necessary to consider cooperative control without global position measurements. The objective of this research is to design distributed formation control laws for heterogeneous vessel networks without global position measurements. The generic under-actuated surface vessel model is shown here, which is a combination of the kinematic equations and the dynamic equations. We don't assume any particular structure for the internal dynamics for the vehicles and allow them to have non-identical dynamics. Then, we model the communication among vessels as a directed graph. We assume that the communication graph contains a spanning tree and is time invariant. Next, we define the desired formation for the networks by a set of 3-dimensional offset vectors. For example, the desired configuration for the vehicle I is determined by its neighbors J and K, and these offset vectors. It is noted that these offset vectors also contains not only the position, but also the orientation for each vehicle. So, the formation control problem is defined as, without global position measurements, design control laws for all the agents such that all the signals in the closed-loop system are uniformly bounded, and all the vehicles converge to the desired configurations given by the desired formation. Before the design, the first thing is to distinguish the feasible formations. Note that desired formation cannot be assigned arbitrarily for under-actuated networks. Here's a fact. For vehicles with 1 degree of under-actuation, the offset vector, which is the desired formation, can only be independently specified for 2 elements. We specify the first 2 position elements for the formation. So, the desired position is given here. Then, the feasible orientation trajectory is forced to obey the non-holonomic constraints as agent I. And here is a constraint, which is a first-order ODE with respect to θi. So, by numerical integration of the ODE, the feasible orientation offset vector is selected here. We emphasize that no global position information is required in generating the feasible offset vector, and only velocity and acceleration information is used in this procedure. Also, the formation is achieved if the agent converts to the desired configuration. And in the control design, we will use these differences to design feedback, and only relative position is required. Then we start the design by defining the formation area Zi using this transformation, where J is the orthogonal rotation matrix, and lambda here is a diagonal and a Hurwitz matrix. Note that ZI converting to 0 implies this part converting to 0, and this part is actually a stable linear system. So ZI tends to 0 implies the configuration error tends to 0 too. The aerodynamics is given here, and under this preliminary feedback, the reduced order aerodynamics can be written as this system, where psi is given by this equation. This error system is the basis of our control design. We identify two structural properties of the reduced order system. The first one is that the drift part, which can be written as this form, has a linear model reference adaptive control structure. Assume that this psi is 0, then this is reminiscent of the linear MRAC system, which is shown here. So for this system, if ABC is passive and this phi is continuous and bounded, then the origin is exponentially stable if and only if phi t is persistently exciting. So for our system, since it has the same structure, it is exponentially stable if and only if the angular velocity is persistently exciting, where A matrix may be introduced by U1I. And the second property is that the error system has a cascade-like property. That is, the nominal part is reminiscent of a cascade system, which is shown here. So for this cascade system, the system sigma 2 is decoupled from sigma 1. Here we have similar structure for the error system. That is, the third equation is decoupled from the first two equations. And if ThA14 goes to 0, then this interconnection term, psi I goes to 0. So the aerodynamics is a cascade-like system. From the discussion above, different traditional control methods may be applied here. For example, the sliding mode control, backstepping, or even linear feedback. However, these designs require that the leader's angular velocity is either separated from 0 or persistently exciting. This conditions means if the angular velocity is small, then there is no control action in the under-actuated ThA2I equations. So this is a singularity issue. For example, if the desired formation path is a straight line, then the angular velocity will be 0. So traditional methods cannot be used here. To solve this problem, we proposed the following nonlinear time-varying controller, which is a combination of the linear controller with a nonlinear term. It is noted that psi and ThA3I are of the same order when ThA3I converting to 0. That is, if ThA3I converts to 0 exponentially at a rate gamma, then psi converting to 0 exponentially at the same rate, and this term is bounded. And under this control law, the aerodynamics are transformed into this form. And then again, we identify the same linear model reference adaptive control structure appeared in the aerodynamics. So this block is A, and this is B, and this is C. But in this case, the time varying function here is not only the angular velocity, but also contains psi over ThA3I. And the persistently exciting condition for these terms finally are transformed to this condition. That is, if one of the angular velocity and the forward velocity of the leader is persistently exciting, the aerodynamics are exponentially stable. So we have the main result here. Consider a group of heterogeneous planar vehicles, and the aerodynamics are given here. If the disturbance terms have linear growth bounds with respect to ZI, then with positive gains, the origin is global asymptotically stable. And if the disturbances are bounded, then the solutions are globally atomically bounded. So with this controller, the singular Fourier formation control problem is solved. Okay, let's look at the simulation result. In this example, we assume there are three different vessels in the network. Two of them are with linear damping model, and the third one is with this nonlinear damping model. We assume that the desired formation path is this shape, and the desired geometric pattern is a triangle. As can be seen from the simulation, the three vessels start from these positions, and the black path is the leader, and the blue path is the follower, agent 1, and the red path is the follower of both the leader and agent 1. So in the simulation, even though the leader's path is a straight line, the formation is still achieved. At this point, I want to conclude my talk. In this work, we present a singular Fourier formation control framework for heterogeneous surface vessel networks. We emphasize that the control laws don't require the global position measurements and are distributed. Also, the design is based on the structural property of the aerodynamics and is an integration of several nonlinear design tools. For future work, we want to extend the design framework to three-dimensional vehicles, and also consider more practical problems such as switching topology and time delays. And thank you, and all of your questions are welcome.